Hello AP Physics students. Welcome back from spring break. This is Mr. Kennedy. I hope you had a nice spring break. Hope you got to spend some time just hanging out with your family and everything. Today we're going to start our first lesson on electromagnetic induction. This is our last unit in AP Physics. And you should have done the lab. There was a lab yesterday that you should have done to take a look at this. And the whole idea that we're trying to get around here is that we know that electricity produces magnetism, but how does the opposite happen? How does magnetism produce electricity? How do we generate electricity from all this? And in the lab, you should have seen that certain changes produce electricity. Certain changes produce a little light bulb to light up. And last year you examined this in this way. You examined something called magnetic flux. And the magnetic flux, which is really similar to electric flux. Last year you said it was the magnetic field times the area of a certain loop of wire times the cosine of the angle in between them. This year we get a little bit more sophisticated, and this year the magnetic flux is the integral of B dot dA. Now, you might remember from Gauss's law that the electric flux was the integral of E dot dA. So this is the same thing except for magnetic fields. And for this to happen here, we have to have some amount of magnetic field that passes through an area. That area is typically a loop of wire or some region or something like that. And as long as change happens, as long as there's a change to the magnetic flux, then you'll produce electricity. So as long as we could change the magnetic field, you'll produce electricity. As long as we can change the area, you'll produce electricity. Really remember that this dot product adds in a cosine of theta. That's where the cosine of theta comes in up here. So you could really change three things. You could change the magnetic field, you could change the area, or you could change the angle. In other words, flip the wire into some kind of circular pattern or oscillate it. And then you're going to produce electricity. So very similar to last year. Last year it was BA cosine of theta. This year it is the integral of B dot dA, the magnetic flux that magnetic field that passes through some area. Now keep in mind that many times the magnetic field does not depend on the area. So oftentimes this equation will just revert back to what you did last year, where it's just the integral of B dot, or just BA cosine of theta. So we'll see some situations where it does depend on the area, the magnetic field does depend on where you are in there, but that's not going to be that common in AP Physics. So once you've found that by changing one of these things, by changing the magnetic field, by changing the area, by changing the angle, you produce electricity, well, that introduces us to our next right-hand rule. And this is the last right-hand rule that we really need. There's three. And if you remember, our first right-hand rule was thumb was the direction of current, fingers were magnetic field, and palm was the force. That's the force on a particle or the force on a wire. The second right-hand rule is thumb in the direction of current and fingers produce the magnetic field. Those are the same. But this last right-hand rule is a little bit different. This last right-hand rule tells us which way current is generated. And what we have to do is think about what's happening to the change in that's producing this change to the magnetic flux, and it will always want to oppose the change. And I'll give you a quick way of looking at it here in just a minute, but let's take a look at a couple examples. So our first example, let's say that we have a magnetic field coming out at us. Here's a magnetic field coming out of the page right here. Make one more set there. So there's a magnetic field coming out of the page. Now, let's say we have a loop of wire here, and we're bringing it into the magnetic field. Well, the third right-hand rule is going to help us determine which way that that change to the magnetic flux will produce a current in the wire. So if we bring it from here, where there's no magnetic flux going through there, there's no field going through this loop, and then we get to here where now there is magnetic flux going through the loop. Here's what the right-hand rule says. It says that right now you had none. There's no magnetic flux through here. Then you had a magnetic flux coming out of the loop at you. Well, what it's going to do is it's going to make a resistance to the change. So because you went from nothing to something coming out, it produces a magnetic field, a change in the magnetic flux the other way, in other words, down into the page, and curl your hand then. So in this case, the current would flow around in this direction. In this case, it would flow around clockwise. So if we then remove this from the magnetic field, now we take it out of here. Now we had a magnetic flux that was coming out of the page, and we take it out. Well, now it wants to resist the change. So it had magnetic flux coming out through the loop. Now it has nothing. It wants to keep magnetic flux coming out. So curl your hand, and we see that this case is counterclockwise. But let's actually go back and look at a much easier way to look at it. Since it is going to resist the changes to the magnetic flux, just ask yourself this question. Is the magnetic flux through the loop getting bigger, or is it getting smaller? In the first one, the magnetic flux through the loop is getting bigger. It's going from nothing to magnetic flux coming out, so the magnetic flux through the loop is getting bigger. Whenever you have a situation like this, point your thumb against the way the magnetic flux is increasing. So nothing to something, so it's increasing out of the page, so point your thumb into the page. So point your thumb opposite the way the magnetic flux is pointing. Whenever you have a flux where it is decreasing, and you can see from here to here it is decreasing, when you have a magnetic flux coming through or out of the page and then have nothing, point your thumb in the same direction because it wants to keep what it had, and then it points the other way. You should have some kind of consistency here where I see that when I bring it in, now that I'm getting a magnetic flux going one way, when I take it out, it should point the other way. So look for situations where you ask yourself, is the magnetic flux getting bigger or smaller? If it's getting bigger, point your thumb in the opposite direction. If it's getting smaller, point your thumb in the same direction, and then curl your hand. Your hand is going to be the way that the current is going to flow. Now, let's examine that a little bit. Thumb is now pointing in magnetic field, actually magnetic flux change, and fingers are now current. And you might say, well, isn't that backwards what we've done before? And it is, because the process is backwards. This time, we're using magnetism to produce electricity, where before we were using electricity to produce magnetism. So again, thumb is the way the magnetic flux is against the way the magnetic flux is changing. Fingers are the way the current is going. So let's take a look at another one. Actually, we'll take a look at a few more. If we take a look at the next one, I've got a magnetic field that points straight up here. And now I'll take a loop of wire, make it a little square loop of wire this time, and I bring it into the magnetic field. Right now, there's no flux that passes through here. But then once I get in here, I notice that also because, we're not catching the rain, as we used to say in electric field, nothing is actually passing through here. Now I still don't have any field. This means the current is 0. I'm not going to have any current because I haven't had any change. I have no flux here, I have no flux here, so there's no change. I remove it from the loop, or from the magnetic field, and now I also have no change again. I went from no flux here to no flux here, so no current is going to be induced. So it's not just having a magnetic field, it's having a change in magnetic flux. There was no flux here, there was no flux here, there was no flux here, there's no change, the current won't be induced in this thing. Where in the last example we had flux that was actually passing through it. So you have to be careful to make sure that flux actually does pass, otherwise you won't have any change to any of the things that are happening. Now let's take a look at one more. What if I had a magnetic field pointing into the page? So there's a magnetic field right there. And then, let's say I have a loop, and I stretch the loop. I take my hands and I stretch the loop out and I make it bigger. So I made the loop bigger here. Well, let's see what happens. What happened in this case was I had a magnetic flux that was going down through the loop. There was flux going into the page. But then I opened this loop up bigger, and now there's more flux going into the page. So to resist the change, I now have to point my thumb against the way that the flux is pointing, because the flux is getting bigger, so I want to resist that change. So my thumb points up this time, curl my hand, and now I see that I get a counterclockwise current that goes through there. Well, what would happen if I again took this and I scrunched it down back to where it was? Now what happens if I make it smaller? If I make it smaller, then what's happening is I have flux going into the page and there's less of it going into the page. So I point my thumb into the page. Again, you always point your thumb in the direction of opposing the change. Because this tried to get smaller, I point my thumb in the same direction, curl my hand. Now this points clockwise. So remember, point your thumb with the magnetic field. If the magnetic flux is getting smaller, point your thumb against the magnetic field if it's getting bigger. Again, you're trying to oppose the change in each case. And that's our third right-hand rule. The first two are about what happens with magnetic fields and the forces and the magnetic fields that are generated by current. This one is what happens when you have the electricity coming from magnetic fields. And this comes from a law called Faraday's law. And Faraday's law says this. It says that the voltage generated, which they typically call EMF. I'm not a big fan of the EMF idea because it really is equivalent to voltage and it really is the same thing. It's just the way it's generated. But they like to call it EMF very regularly on the AP test, is negative N times the time derivative of the flux. So what does this mean? This means first of all, let's look at the negative sign. The negative sign, this really represents Lenz's law. And Lenz's law is what we just did. Lenz's law is the part that says that there has to be an opposition to the change in flux. That's what's generating it. So you don't get something that keeps building on itself. You keep getting something that opposes you. That's really based on conservation of energy. This is the number of loops. And this is what's changing. You have to have a changing flux for there to be a voltage generated. Otherwise, there's not going to be any voltage generated. So negative, so you're opposing whatever change happens, the number of loops, and this is the change in the flux. The faster it happens, the more you generate things. But I don't like to use this version because why bother substituting it in? I just like to say that the voltage is going to be negative N, the derivative of the flux. Now, some people will say right there, they'll say, well, wait a minute, isn't that the derivative of an integral? Doesn't that just bring you back to where you started? Well, no. The problem is that this is a time derivative, but this is with respect to area, so they don't just cancel and bring you back to the original idea. But let's take a look at a really simple problem with this, and sometimes it'll get more complicated. We'll take you through that in the next couple days. But let's take a look at a really simple example of this and see what happens. So let's say we have a magnetic field, and that magnetic field is coming out of the page. So here's the magnetic field coming out of the page. And inside of there is a loop of wire. And we'll say it's a nice square with side length of 0.1 meters. So there's a loop going through there. Now what happens is, over the course of time, the magnetic field increases. So in this case, the magnetic field starts out at 1 Tesla and increases to 5 Teslas in 2 seconds. So the question is, what's going to happen in terms of the voltage that's generated here? Now, given that this is a loop of wire, I'm going to say that this has also a resistance to it. That this will have a resistance of 0.5 ohms. So it's just a wire, so a little 0.5 ohm resistor. But let's see what happens first. We see that the magnetic field is going to increase from 1 Tesla to 5 Teslas in 2 seconds. So there's magnetic flux coming out of the page, and it's getting bigger and bigger and bigger. So that means that we'll have to point our thumb into the page, curl our hand, and the current will actually flow clockwise in this. Because again, I point my thumb in the direction to oppose the change, then curl my hand. But when we do this, let's see what happens to the voltage and then the change in flux, etc. Now in this case, we're assuming that it's going to go from 1 to 5 Teslas uniformly, or we can just find the average. Either one is going to be okay. But we look at Faraday's law, and Faraday's law says the voltage is going to be negative N, the derivative of the flux. So there it is. So let's see what happens with the voltage. So first of all, the voltage, negative N. Okay, that's just -1. We only have one loop in this situation. Now it's the derivative of B dot dA. Well, this is really going to be the change in magnetic field times the area over time. So this magnetic field, and we'll just do final minus initial to find the change, but it's really change in magnetic field times area. The cosine here is just going to give us a 1 because it's going to be 0. So we really just need to find the change in BA, cosine of theta, over time. So change in magnetic flux over change in time. So let's see what we get. And we just have some simple values, so -1. What we start with is 5 is the magnetic field. So this, we're doing a change here. That's 5 Teslas times 0.1 meters squared minus 1 Tesla times 0.1 meters squared. And we didn't have to worry about the cosine of theta again because that was just a 1, divided by 2 seconds. So when we do this out, what we're going to see is we have 5 times 0.01, and we have 1 times 0.01. So what we're going to see is that the voltage is going to be negative 0.04 Tesla meters divided by 2 seconds. So what we're going to see is that we have negative 0.02 volts. We're going to get 0.02 volts generated in this piece of wire that we have here. Now, because this has a resistance, this is the voltage, this is the resistance, so what we're going to see then is voltage equals current times resistance. If the voltage is 0.02 divided by 0.5, we get a current that is 0.02 divided by 0.5, so that we get a current of 0.04 amps. And I'm not going to worry about the negative because I've already said which way it actually goes. But this is a typical kind of example where you have the magnetic field changing, and that magnetic field gives you a certain voltage and therefore a current. And again, the right-hand rule comes into play all the time here, so be careful with that. So what you should try now is Unit 13, Worksheet number 1, problems 1 to 3, and see how that goes. and email me if you have questions. And good luck, everybody, and I'll see you tomorrow with the next part of this lesson. All right, have a good day, everybody.